This video looks at the idea of gravitational redshift and how it describes the change in frequency of a light signal using the scalar product of a four-wave vector with the four velocity of an observer who is located at the point of emission or reception. It shows how this equation can also describe the energy of a particle or photon in both special and general relativity, and goes on to use this result to determine the ratio of the frequency of a light wave at the points of emission and reception in various spacetimes where the emitter and receiver are moving or stationary. Right, so gravitational redshift refers to the change in wavelength of electromagnetic radiation as it moves in a gravitational field. Now, all problems in special and general relativity concerning redshift are governed by the following two properties. And this comes from Wald's book, 1984. Light travels on geodesics, and the frequency f of a light signal with wave vector k, as measured by an observer with four velocity u, is f equals minus k dot u is equal to minus k subscript mu times u superscript mu. So covariant index here, contravariant index here. Now, where the four velocity is given by this object here, which can be rewritten as this. Alright, now, if we have a look at the four-wave vector, its components are made up of the angular frequency omega over c, and then the four spatial components of the wave vector. And these can also be written as 2 pi over c times the period t. And then the spatial parts of the wave vector, 2 pi over lambda in the x direction, if you like. If we're in flat space, that would be the x direction. 2 pi over lambda 2, that's in the x2 direction, 2 pi over 3, x3 direction. Now, in flat space-time, they would be x, y, and z, the wavelengths in each of those directions. Using the flat space metric, we can lower the upper index. So, by using the flat space metric, eta mu nu times k with the contravariant index mu, and then we can lower that. And that just gives us the same object, but with minus here and all of these indices here. And that's just this object over here. Same thing. In flat space, both the contravariant and covariant forms are the same. That is, the upper and lower index will be the same in flat space. Different in other curved spacetimes though. To show that our scalar product has the dimensions of 1 on time, and so this expression is a suitable expression for the frequency of a light signal, then we just need to do some dimensional analysis on it and just look at the units, the dimensions here. And with this scalar product is this object here, and if you have a look here, gamma is dimensionless, and c over c cancels out here, and so it gives us this object down the bottom. So gamma, as I said, is dimensionless. If you look here, 2 pi is scalar over the time, so 1 over time. Here the lengths are, here the units are lengths and lengths. They cancel, and this becomes 2 pi scalar, that is, over units of time. And so all of these are 1 over time in units. So that's a reasonable expression. It does give us the frequency in terms of units, in terms of dimensions. So it's a reasonable expression to use. Alright, now the energy of this photon, as measured by the same observer, E, is h bar times f. And from the previous page, we can see that's minus h bar k subscript mu, u superscript mu, or minus h bar k dot u, the four velocity. Just remember the four velocity is that of the observer, who records the frequency of the light wave at the point of emission or the point of reception, and so they are at the point at which the measurement is performed. So that is the four velocity of the observer at the point of emission or reception. But the momentum of a photon is given by here are the components, E over c, P1, P2, P3, so it's the momentum 4 vector, and that can be written as h bar times k mu before. Also, in terms of for a photon, the form momentum obeys this relation here. The scalar product with itself is 0. Now, we can lower the index, so in this case we'll use a flat space metric here just to show that. And this relation is going to apply both in flat and curved spaces. And so we have this object here, which gives us this. The energy of the photon can be expressed as minus h bar, k subscript mu u mu, that's the scalar product, or this, as we've seen now, is the momentum with the lowered index, so minus p lower index mu, dotted with the four velocity vector, that's object, or minus p dot u. Right, the energy of a particle or photon measured at the site of the particle or photon by an observer with some four velocity is given by E is minus p dot u, the four momentum dotted with the four velocity, and that be the particle or a photon, so a particle with mass or a massless particle. Now the result is valid in both special and general relativity, where the only difference is in the metric chosen to perform the above contraction. So in the flat space here, in the special Minkowski space, flat space-time, eta mu nu, and in other space-times, curved space-times, we use g mu nu. Right, that gives us this object in both cases. Now we can use this result to determine the change in the frequency of a photon between its points of emission and reception, as measured by some observer in a gravitational field. I have to point out though, the observer is at the point of emission and another observer at the point of reception. So I just need to be aware of that. We'll see that shortly. So here is an emitter following some world line, x em emitter, and it's measured according to its proper time, tau emitter. And over here is the receiver following its own world line in blue here, and that world line is given by this path here, parameterized in terms of its proper time. And so x subscript receiver, REC, and its proper time as it measures tau subscript receive. Both the emitter and the receiver follow their own world lines in some general space-time with metric g mu nu, and the world line of a freely falling object, such as a planet orbiting a star, is a geodesic. Now the four velocity applies to both whether you're talking about a geodesic or some other non-geodesic world line. Now for massless particles, we know that the four velocity dotted with itself is 0. For massive particles, particles with mass, the four velocity dotted with itself is equal to minus c squared, depending on which signature metric you use. The metric I'm using here is the minus plus 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 1. Alright, now, so for the emitter and the receiver, its four velocity is given by this. U for the emitter and V for the receiver. So it just separates them so you know which one I'm talking about. That four velocity is tangent to its world line. At all points on the world line, the four velocity is tangent to it, which is shown by these red arrows here. Alright, now, this name event 1 is where a photon is emitted, and at some event here, some point in time and some location. And over here, the same photon is, at event 2, is recorded by a receiver with some time and location. The momentum, the form momentum of the photon at emission is here, and the form momentum of the photon at reception is here. Alright, now photons travel along geodesics, of course. Now at event 1, an observer measures the energy of the emitted photon to be E1 equals h bar times F1 is equal to minus P emitted dotted with the four velocity of the observer at the point of emission, and this is the form momentum of the photon at the point of emission. Now at event 2, an observer measures the energy of the received photon to be E2 equals h bar F2, and that's minus the momentum of the photon at reception, as measured by this observer with this four velocity. Alright, the ratio of these two energies is E2 on E1 is h bar F2 and h bar F1 is just F2 on F1, and it's this object here over this object. So this inner product, scalar product, over this inner product or scalar product. In a gravitational field, these two frequencies will differ due to the redshifting of the photon as it travels from the emitter to the receiver. When we say redshifting, it can also be blue shifted too. So, and that will depend on the circumstances involved. So in a Schwarzschild geometry where a photon may be emitted close to the mass and then moves outwards, we expect the frequency to be redshifted. if it were falling inwards, you expect the frequency of the photon at the point of reception to be blue shifted compared to its point of emission. If we know the form momentum at emission, then we can calculate the form momentum at reception, because photons follow geodesics that satisfy. Here's the geodesic equation in terms of the form momentum, that's 0, and P mu is m u mu. Now m u mu will be, I should point out that's for particles with mass. We'd be better off using h bar k superscript mu as our form momentum for a photon. So just be careful here, because this really is more appropriate for a particle of mass. Right, now we can produce a simple equation if we allow the spatial coordinates of the emitter and receiver to remain fixed. So let event 1 be now the emitter at this coordinates, and the form momentum of the emission will be this object here, and the forward velocity of the observer will be this object, because what we've done now is the receiver and the observer at emission and the observer at reception are stationary. They're not moving. The emitters and receivers are fixed, and so the forward velocity of the observer at emission is this object here, spatially no change in position. And event 2, the reception of the emitted photon, will occur at these coordinates, and the momentum there will be this object here, where the observer at the receiver has this forward velocity, so the receiver is fixed. Now, from this relation, g mu nu u mu u nu is minus c squared, scalar product of the forward velocity of an object with mass in some general space-time will be equal to minus c squared. So from that we get, because we're talking about the forward velocity observer here now, not the photon, we get g00 is u0 u0 if it's equal to c squared, because the g00 term will be negative. And so when we work that through, if you think about your metric, that'll be negative in this signature, so that'll cancel out the minus here. And so u0 will be c on the square root of g00. Now, the ratio of the frequency of the emitted and received photons is now f2 and f1. It's this object over that, which is, now we can replace the observer and u observer by these relations respectively, and that gives us this expression here, p0 received over p0 emitted times the square root of this object. Now the ratio of the two frequencies for an emitter and receiver that are both at spatially fixed coordinates is given by this object here. So there's our first major result. Now, if the metric is stationary, meaning that it does not depend upon the x0 coordinate, then we have the partial derivative of the metric with respect to the x0 coordinate, the time coordinate, is 0. And this means there exists a killing vector in the direction of the x0 coordinate. Now this vector is tangent to the congruence of the coordinate curves for this coordinate x0. It has the form zeta, I think it is this object here, gives us this unit vector here. Now killing vectors correspond to quantities that are conserved along geodesics, and so this can be expressed as a condition where d lambda, remember we parameterized our curves according to lambda, and the killing vector with the forward velocity, that inner product, is same as this inner product here, the indices swapped around, is 0. Alright, give a bit of an example. Let's foliate space-time into various hypersurfaces. So this is a hypersurface at one point in time, and this is another spatial hypersurface here at another time, so at a later time t2. So this is foliating space-time, and we see here the time coordinate curves here moving through, and a congruence of them, and meaning that there's no overlapping there and they fill the space. And tangent to those curves, those coordinate curves, or time coordinate curves, are the killing vectors. There we go, the killing vectors. Now let's move on. Let's put in our geodesic. There we go, this is our geodesic, and what we find is along this geodesic we have, at all points along it, the killing vector and the scalar product of the killing vector with the fall velocity is the derivative of that, total derivative with respect to the parameter lambda, is 0. So the fall velocity is tangent to the geodesic. That's this vector here, which is tangent to the geodesic at all points along it. And the scalar product of the killing vector with the fall velocity is constant all the way along there. So this angle between these remains constant all throughout the journey there along the geodesic. That's the relationship there. Where the tangent to the geodesic curve x mu of lambda with affine parameter lambda is this. Now, this right-hand side of this equation can be related to the momentum of the photon through the normalization condition for the momentum of particle with mass. So here's the fall momentum, normalize that. We get this minus m squared c squared, so that's for an object with mass. Now we cannot use the proper time tau when dealing with photons, as our affine parameter the tau vanishes along a null geodesic, that is ds squared is 0 along null geodesics. And so now we define the parameter lambda to be lambda is tau on m, which remains finite as m approaches 0, in the limit as m goes to 0, so that d tau equals m d lambda still remains defined. And so what we do now, take the inner product there, p dot p, with this object here, and the familiar form momentum, but this time now we're going to replace d tau with m d lambda, and we get dx d lambda. Dx d lambda is minus c squared. And so what that tells us is that we now have with this scaling that p mu is dx mu d lambda is u mu. Now, so we can write the momentum in terms of this fall velocity here, just by this rescaling we did earlier. Now returning to conserved quantities along geodesics, d lambda of this object here, and in our particular case, the killing vector only has a component in the time direction, and so we're only, when we do the scalar product of this and the fall velocity, we're only going to get the time components involved, the product of the time components of each involved. So we get d lambda, killing vector, the 0 component of the killing vector, and the 0 component momentum. Right, as we can see, the 0 component is just 1, so it's d lambda of the momentum component, the time component of the momentum, and we see that that's 0. And that tells us something about this time component and momentum. This tells us that the time component of the photon's momentum is constant along the geodesic it travels along, and so p0 at event 1 is p0 at event 2. And then returning to our two observers at spatially fixed coordinates, we have f2 on f1, that's event 2, event 1 is the receiver over the emitter times this, is this over that, is p0, p0, which they're the same, they cancel out. We're left with just this object here, the square root of the 0, 0 components of the metric at each of the points, at emission and reception. Alright, so the ratio of the emitted and received photons in a general space-time where the emitter and receiver are at fixed spatial coordinates is given by this object here. As an example, let's look at how this can be used in a Schwarzschild space-time with metric. This object here, the Schwarzschild metric. And if we have a look at it, there's our mass, and here's the point of emission, here's the point of reception, and so F receiver over F emitted is this object here, and put in the 0, 0 component at emission and the 0, 0 component of the metric at reception. Here we go. And this can be written as F received over F emitted is this object here. When we do a little bit of algebra, cancel out minus signs and fix this up. Just rearrange a little bit, make it look a bit nicer. And it gives us this object here. Now this distance here is less than this distance here, as you can see from the diagram. Right? And so the frequency here is going to be smaller here. The frequency here will be greater than the frequency here. So F received will be larger than, smaller than R emitted than at R emitted. Let's get that bit mixed up. Alright, now a summary. In any space-time with metric g, mu, and u, the ratio of the frequencies of a photon at emission and reception, as measured by observers present at the location of both events and moving freely with respect to each other, is F2 and F1. Is this over this? That's our first result. If the emitter and receiver are at fixed locations, then we can do this. Alright, so that's all we require, they're just at fixed locations. Our next step now is, if the emitter and receiver are in a stationary space-time, that is, the metric is independent of the time coordinate, then it becomes even simpler. It becomes this object here, and in particular in the Schwarzschild space-time we have this object here over this object. That's the important result, and this means that you have so that you have at reception the frequency will be smaller, less than at emission, meaning that the at reception the photon will have a longer wavelength, lower frequency, than at emission where it will have a higher frequency, lower wavelength, and so it is redshifted as it moves away from the mass shown on the previous page. And that brings us to the end of that.